Hi, let's now close Module 8, Verification of Renewable Energy Forecast, with its third block, Verification of Probabilistic Forecast. Remember that we previously discussed deterministic forecast, which were single-valued trajectory into the future, for instance for a lead time of 24 hours ahead, telling you power generation is going to be this value for this time. Now we're going to deal with probabilistic forecasts, which are related to a probabilistic statement, which means telling some of the characteristics of the random variable power generation at that time. These probabilistic forecasts may take the form of quantile forecast, interval forecast, and density forecast, which are the products we're going to consider here. In practice, we need first to start with some visual inspection of the forecast. We did that for the deterministic prediction. We expect to start the same way with probabilistic forecast. Therefore, here I show the same example we had in the previous block with a forecast for lead times between 1 and 48 hours ahead, and power here expressed between 0 and 1. It's normalized, and you could reinterpret 1 as the nominal capacity of the wind power portfolio of interest. In bold here, black, you have the point forecast that we already studied previously. The circles with gray lines between them are the observations that were collected a posteriori, and now all these intervals around are interval forecasts with different nominal coverage rates, and altogether they describe the densities for the random variable power generation at each and every lead time. Looking at this single plot, can you tell whether this forecast is good or not? Actually, you may infer from previous assessment of the point forecast in a similar way. The trends seem to be right. So the probabilistic forecasts seem to follow what actually happened, and a good sign is that this observation seems to be within the various envelopes most of the time, at least for the widest one. And if you go closer and closer in terms of probability, so for lower nominal coverage rates, obviously the observations are not within, but this lower nominal coverage rate actually means that the probabilistic contract is that we only cover the observation, let's say 10% of the times for the tighter intervals. Another thing we can infer from this plot is that the forecast seems to inform us that there's going to be low uncertainty at the beginning, here let's say towards the middle because there's low power generation predicted, but then that the uncertainty is going to be very high towards the end of the forecast horizon. But in terms of the forecast being good or not, it's not really clear. It's actually very difficult to say when looking at single forecasts, probabilistic forecasts, whether these are good or not so good. Instead, we have to go through a thorough quantitative analysis. Also, when it comes to probabilistic forecast quality, the attributes are quite more complicated. So I call it here, how do you want your forecast? You may want your forecast to be reliable. Reliability, which is also called probabilistic calibration, is about how you respect the probabilistic contract. You may want your forecast to be sharp. Sharp is here in the sense of informative. So you want these interval predictions to be as tight as possible, since that means you're pretty sure of what's going to happen, since you give a clear trajectory for the future. You may want your probabilistic forecast to be skilled, and skill here is to be interpreted in terms of all-round performance and higher quality than some benchmark. Then you could also say, I want my forecast to have high resolution, and resolution there is about resolving a situation with various type of uncertainty levels. So the uncertainty might be high when the wind comes from west, the uncertainty might be low when the wind comes from east. You want this kind of varied information. There are actually more and more attributes that you may consider, but the most commonly seen in practical forecast studies would be the first 4 that we have here, and we will focus actually on the first 3 in the following. First of all, probabilistic calibration or reliability is about respecting the probabilistic contract. For a quantile forecast, which we denote Q hat t plus k given t, so it's for time t plus k but issued at time t, there is a nominal level alpha here, and let's say this nominal level is 0.5, so we consider the median. If we do so, then that means we expect that the observation yt plus k are to be less than this quantile forecast 50% of the time. That's the contract. That's the definition of the quantile forecast. In parallel, for an interval forecast, which we denote I at t plus k given t and with a b being the nominal coverage rate, let's say b equal 0.9, that means that we expect the observations are to be covered by this interval 90% of the time. Going more into detail, this kind of interval is actually formed by two bounds, and these bounds are two quantile forecasts which have nominal proportion we can deduce from this nominal coverage rate. An interval forecast with nominal coverage rate beta equal 0.9 is composed by a quantile forecast, the lower one, with nominal level 0.05, and by another quantile forecast for the upper bound with nominal level 0.95. So actually, if we want to evaluate this interval forecast, we can also evaluate the calibration of the two quantile forecasts that form this interval forecast. Eventually, for predictive densities, these are composed by a number, let's say m plus 1 of quantile forecasts with different nominal levels of increasing value, so alpha 0 to alpha m. And again, all these quantile forecasts can be evaluated individually. An example could be that all these nominal levels go from 0, then 0.05, 0.1, etc., till 1. To do that, since it's about a probabilistic contract that we evaluate a posteriori, we can take a frequentist approach. That means we simply count. How are we going to count? First, we need to define a quantity which we call the indicator variable. This indicator variable is going to be denoted psi t plus k with alpha, the nominal level. Here, this is the corresponding quantile forecast. So for this variable, we're going to define that is going to be equal to 1 if the actual observation is less than the quantile forecast, and that would be a hit, and it's going to be 0 otherwise, and that would be a miss. In a mathematical manner, we can write it in a more compact form with this unitary function. Then by counting the number of hits and misses over the set of forecasts, so let's say we are forecasting over 6 months and we are collecting a lot of forecasts for all these lead times of interest, then we can obtain the empirical level of this quantile forecast. And this empirical level, which we denote AK alpha, K since we're going to calculate it for a given lead time. So for a given lead time, we collect all the forecast, all the observation, we calculate this indicator variable, and then we're going to take the mean of the value of the indicator variable over the set of quantile forecasts. So AK alpha is equal to NK alpha divided by big T, where NK alpha is the sum of hits. So the sum of the times where the observations were below the quantile forecast. There is a way to summarize all these assessments, and it's with a reliability diagram. We have an example there on the right, which we'll discuss shortly. So here we're going to evaluate our probabilistic forecast for the wind farm of Klim for this period between the 1st of July 2002 and the 31st of December 2002. We have predictive densities that are composed by quantile forecasts with nominal levels 0.05, 0.1, etc., till 0.45. Then we jump to 0.55, etc., 0.9, and 0.95. So that's 18 quantile forecasts with different nominal levels. We evaluate these quantile forecasts one by one, and we calculate their empirical levels, which we report versus their nominal levels. And this is what we get here with this reliability diagram, we have here the nominal levels of the quantile forecast, so that's the probabilistic contract that was expressed originally, so it should be nominal level 0.2, for instance, or 0.4, or 0.6, etc. And then what we report here is what was really observed, so the empirical level of this quantile forecast, how much they covered the observations on average. Obviously, the closer to the diagonal, the better, since for a perfect, an ideal case, you would have an empirical level which is exactly equal to the nominal level. You fully respect your probabilistic contract. In this case here, the assessment we make for Klim for a probabilistic forecast is summarized by these circles in bold and black with lines between them, and you can see that the empirical levels of the quantile forecast are very close to the diagonal, to this ideal case, so actually our forecast seems to be quite reliable. Besides reliability, we mentioned sharpness. Sharpness is about being informative, it's about concentrating probability. If you think of it, a perfect probabilistic forecast would give a probability of 100% on a single value, and that would be the value that we observe a posteriori. Therefore, the sharpness assessment boils down to evaluating how tight, how narrow the predictive densities are. In practice, that means that we define the width of a given interval forecast, I hat t plus k given t, with empirical coverage rate beta, is defined by the distance between the two bounds. This distance delta is equal to the distance between the lower and upper bound of the interval. This is the upper bound with alpha bar over, and this is the lower bound with alpha bar under. So we simply calculate the distance between the two bounds of the intervals. Eventually, as we have calculated this distance for different lead times, for different nominal coverage rates, etc., we can summarize the sharpness of this interval forecast by calculating their average width over the evaluation period. And this average width, delta bar beta, for a given lead time k, is here, you see, the average of the distances of the widths of the intervals that we calculated previously. Here is an example, also for the case of Klim, of sharpness evaluation. We have predictive densities that are composed by interval forecast that we already defined before, somehow with the quantile forecast with different nominal levels, but eventually that means here we have interval forecast with nominal coverage rates of 0.1, 0.2, etc. until 0.9. So we have 9 interval forecasts that compose our probabilistic predictions with these different coverage rates. So here you see we have 9 lines which show the width of this interval, so as a function of the nominal coverage rates. These widths are plotted here as a function of the lead time between 1 and 48 hours ahead, and this is the interval width, which is in per unit, since it's consistent with the original variable we care about, which is power generation. Here the interval width increase with the lead time, so that reflects there's higher forecast uncertainty as we look further in the future, but also something that is intuitive, the width increases as the empirical or nominal coverage rate increases, which is also intuitive if your probabilistic contract would be that you cover the observations more often. Obviously you need to have wider intervals. Eventually, since we have reliability on one side and sharpness on the other side, how would we decide on overall skill of the forecast? This is why we need some skill scores, and they have to be proper so as to ensure we have forecast consistency. And skill scores are like what we introduced before for deterministic forecasts. You saw the mean absolute error, the root mean square error. We need to define scores like that for probabilistic forecasts. The most common skill score that we use for predictive density is the continuous ranked probability score. If you were to look at a given forecast predictive density, this would be, if you take a slice, this would be this blue line here. It's a cumulative distribution function for power generation. here normalized, and here you have the cumulative probability. So this is a forecast for a given lead time for power generation. The perfect forecast in that case would be the red line. I explained you earlier, a perfect probabilistic forecast is to put all probability mass on a single value, which is the observation itself. So in this case, let's assume the observation was 0.45, so power generation of 45% of nominal capacity. In terms of cumulative distribution function, this is how it would look like. It's called a Heaviside or step function, and obviously the probability is 0 until the value of the observation, and then you jump to probability of 1 since now you have observed this value. So that means that we would like our probabilistic forecast to be as close as possible to this red line. If we want that, we can define some kind of measure that looks at how close this blue line is to this red line, and that's what the CRPS does. The CRPS is defined as an integral of the distance between your predictive density, so here in blue, and this perfect predictive density, which is here in red. This distance is squared so that we don't make a difference between when it's above and when it's below. So you have to think of integrating over these areas squared, and that gives you the CRPS. However, this value of the CRPS is for a given pair of probabilistic forecast and observation. Now we have a lot of those. We need to calculate these CRPS values for each and every forecast observation pair, and then we can calculate statistics as we did for MAE and RMSE. So eventually the CRPS core value is given by taking the average over all the predictive density and corresponding observation over the evaluation period. And as we did before, we calculate the CRPS for different lead times, so as the average over all the times we have in our evaluation set of the CRPS values that we calculate based on these distances. Let's look at it for Klim again. We have a CRPS evaluation between the 1st of July 2012 and the 31st of December of the same year. And here, the CRPS values are shown as a function of the lead time. And again, it has the error here, which is normalized, and so it's expressed in % of nominal capacity. The value of the CRPS is here, with this circle and small lines between them. And I've shown here another score, which we'll not study here, which is the NQS, which we may find in some papers or some books. As you can see, the evolution of the CRPS with the lead time is quite similar to what we saw for the RMSE and the mean absolute error. The way to interpret it, for instance, for a given lead time, 24-hour ahead, you can look at the CRPS value and say, well, the CRPS is equal to 7% of nominal capacity. It may sound like it's difficult to interpret, but actually what's interesting with the CRPS is that it's a generalization of the mean absolute error that we use for deterministic forecast. So these two can be directly compared. In the previous block, we mentioned that for this lead time, for instance, the mean absolute error was of 8% of nominal capacity. Here, the CRPS is of 7%. So that means somehow that this probabilistic forecast have higher quality than the original deterministic forecast. Thank you very much. Now I would like to invite you to use the self-assessment quiz to check your understanding.